Hello, everyone. Welcome to Nicoya's first OpenSPR webinar series episode here. My name is Mike Piazza, and I will be going through the topics of today's presentation. For today, we're going to be going over planning your next OpenSPR experiment. We'd just like to thank you for joining us today. We understand that we are dealing with some pretty worrying and challenging times in our current lives, and some things have been turned a little bit upside down, but we hope that we are able to at least provide some science background here for you to help you through these challenging times. For today's webinar, if you do have questions, please feel free to write them in our chat beside the window on your screen, and I'll try to address them as we go through this. What we're going to go through today is a presentation outlining all the various steps that we should be considering when planning our next experiment so that when we're ready to get into the lab, we're ready to start working again. For that, I'm going to change over to our little presentation here. And as I said, I will be monitoring our screen. If you have any questions, please feel free to write them on the side chat there. So hopefully we'll be able to take care of all those questions as they come in. So the first thing here is what I said, planning is the experiment so that when we get back into the lab, we're able to get right into doing some work and then hopefully being able to publish this data. What I have here are a few examples of where the OpenSPR has been used in the past to publish their binding kinetics data. So hopefully you'll be able to succeed with that in the near future also. For today's talk, we're going to go over all of these topics here. So we'll have a thorough understanding of each of these, and hopefully you'll have some takeaways for what you should be thinking about for when you're going to be running your next experiments. Our first section will be the background information. So before we even get into the lab, before we even start preparing our samples, we can actually do a lot of background research so that we're prepared for what we're going to be undertaking. So these will include doing a literature search on the binding partners. So these could be, a couple binding partners that you've worked with in the past in your lab, or if you're, trying on a new experiment, then this is a good place to start. So what we mean by this is hopefully you'll be able to search for past information on stuff like binding kinetics. So if there was a theoretical affinity for this interaction, whether that was found via other SPR experiments or ITC, fluorimetry, those binding kinetics will translate very well to the OpenSPR. Another important thing you should be looking for is sample conditions. So what conditions are necessary for these two partners to interact with each other? Is there added constituents needed for the buffer, such as calcium, magnesium, other cofactors? These are all things that should be on the forefront of when you're doing your literature search. And the reason for this literature search is that it's going to help you with choosing which one of these binding partners we're going to immobilize on the sensor surface as the ligand, and which one is going to be used as the analyte. Now, in SPR terminology, we use ligand and analyte to denote the two different binding partners and how they're used in the experiment. So the ligand will always be referred to as the partner that is immobilized on our sensor surface, and our analyte is always going to be referred to as our other binding partner that'll be free-flowing in solution. So to help us with this background search, we have 6 factors that we should be considering, among others, but these are what I would consider to be the 6 more important factors. So the first thing is we should have a knowledge on what the molecular weight of our 2 binding partners are. So and the reason for this is ideally we would like to have the larger molecular weight partner as our analyte. And this will become more apparent when we get into the ligand section of this talk. And this comes down to how the SPR actually functions. So the SPR signal is proportional to the mass on the sensor surface. So if we have a smaller binding partner immobilized to the surface and a larger binding partner coming in as the analyte, this mass or this response will be amplified when that binding event is occurring. And one can also appreciate that if, for instance, say we are using a small molecule as one of our binding partners here, it may not be feasible to use that as the ligand, as it might prevent binding of our analyte to the small molecule. So we'll see that we'll have to get a larger ligand response signal, and we'll get to that a little bit later on. The next factor we should be dealing with is the purity of our 2 binding molecules here. So we would ideally like both biomolecules to be pure and homogeneous. Now this comes down to a few factors. So one being, if for instance we're using carboxyl sensors, then we're going to be using a protein as our ligand. If that sample is not pure, then we'll have a mixed population of different ligands on the surface. And then when we go to do our binding studies with our analyte, we'll see inconsistencies in the binding response curves that we're acquiring. And then this will cause problems with the fits we're trying to get, and then lead to incorrect kinetics that we're determining. Now, for instance, if we have a fairly pure mixture and we're using one of our coupling sensors, which we'll get to also in a bit, then we can potentially purify this further when we couple those to the surface, as anything without the tag that we'll be using for coupling purposes isn't on those other molecules in the solution. They'll just wash off the sensor. The next factor to consider is how many binding sites each of these partners have. So if you have one binding partner that binds multiple substrates, which, then we would recommend that that binding partner is used as the ligand. The reason for that is it'll greatly simplify when we go to analyze this data and fit for our kinetic constants. We'll be able to use a simpler, one-to-one fit or something of that nature, because the analyte in this case will be able to bind to multiple sites on that ligand, but since the analyte itself only binds once, it'll make for a simpler fit when we're going through the fitting. The next factor to consider is, do any of your biomolecules contain a tag? Now, these can be used to our advantage, especially if we're using a capture coupling mechanism. So say, for instance, you have a protein with a his tag or a small molecule or DNA molecule with a biotin tag. We can then use these to immobilize these to a different sensor surface. And another advantage of this is it allows for selective orientation of this ligand on the sensor surface. So this should greatly improve the binding ability of our analyte when we're going to do our kinetic screening. Another factor is the charges on our biomolecules. So this is important for a couple of factors. So one being for ligand immobilization if we're using carboxyl, and another being for non-specific. So what I mean by that is in the situation where we're using a protein and amine coupling to immobilize it to the surface, if we know the PI of that protein, we can take advantage of the inherent charges on that protein and use what we term pre-concentration to aid in our ligand immobilization. Now, we'll touch upon this a little bit further when we go into planning our ligand immobilization steps. Another factor with knowing these charges is if we're using, say, NTA surface or carboxyl surface, the surface itself has inherent charges present on it. And if our analyte in this situation has the opposite charge, then we could be getting nonspecific binding due to that charge-charge interaction. So this will further allow us to plan how we can suppress or block those charges when we talk about optimizing our blocking molecules. Again, we'll talk about that a little bit later, but we should be having these in the back of our head as we're going through our literature search. And the last factor that I would keep in mind is steric hindrance. This would be a factor if we're using like one of our partners is quite large, or if both partners are quite large. If we have immobilized quite a bit of that ligand on the surface and they're packed quite densely on the sensor surface, this could lead to steric hindrance when we're trying to bind our analyte to the sensor surface. Now, ways we can get around this is we can actually lower the ligand density. Now, again, we'll see when we come to the ligand immobilization section, if we need to reach a certain ligand immobilization level, this might not be feasible. But again, this is something that we should be keeping in mind for when we're planning our experiments. So after we've gone through our literature search, this will lead us nicely into then deciding which sensor chemistry we want to use for our experiment. There are quite a variety of different flavors, as we will call them, for sensor surface chemistries that we can use. And hopefully after you've gone through that literature search, you'll be able to decide which molecule you want to use as your ligand and which as your analyte. And then depending on what tags or if it's a protein, this will determine what type of chemistry we want to use. So the three flavors are covalent coupling. So this would be if we're using a protein and we're going to amine couple it to a sensor surface, or if one of our binding partners, the one we're going to use as our ligand, contains a thiol group, we can then couple it to a plain gold sensor. The next one would be capture coupling. So this is where the tags come into play. If we have a biomolecule with a tag, we can then couple it via that tag. And then lastly, ligand capture. So if we're using a liposome or we're trying to do a membrane mimetic type surface, we can use these sensors to create that membrane type layer. Once we've decided on the sensor surface, we'll have to then start thinking about what kind of running buffer we're going to be using for an experiment. So in this running buffer, again, because we've done this literature search, we've looked at what conditions are going to be necessary to enable binding. We want to make sure that that buffer includes all of these components. After we've prepared these buffers, we also want to make sure that we don't forget to filter and degas these. So these become important for the overall running of the experiment on the instrument. The reason for this, for filtering, is we want to make sure that we have taken out any particulates from the sample so it doesn't cause any clogging or buildup in the tubing. Degassing, we want to make sure that there is no microbubbles that will accumulate in the system and then cause bubbles to form on the sensor surface. I see we have a question here. Will this seminar be available for review later? Yes, the full video will be available for access once this webinar is done, and you'll be able to view it whenever you'd like. So one other thing to be aware of when we are preparing these initial buffers for our experiments is these conditions will most likely change with optimization. And we'll get into that once we get into our control experiment design. The reason for this is that what we'll see is that certain things like nonspecific binding or bulk shifts might cause artifacts in our response curves that we're gathering. So we'll have to adjust and adapt to those by changing these buffer conditions. And now the most important thing to remember whenever we're preparing these samples is our Analyte sample buffer and running buffer must match. And we'll talk more about that again when we get into these control experiments, but we want to ensure that that's the case to prevent any errors just due to mismatch of buffer. So some things that often get forgotten when planning a new test are control experiments. So the control experiments are very important, especially when you're going to publish your data, because this is the only evidence you have that supports that what we are seeing is specific binding of your analyte to the ligand. And we want to do these control experiments so that we can make sure that we have, evidence that we're not seeing any false positive bindings. So what we mean by false positive is stuff such as nonspecific binding or bulk shifts in our data. So we'll go through a couple of examples of these. But again, these are certain things that should be also included when we're going to publish our data. We should have our control experiments explained in the methods so that when the reviewers are looking at the data, they can be confident that the data we are seeing is specific binding of the analyte to the ligand. Now, with these control experiments, as we said earlier, we might have to optimize the running buffer. We might have to also optimize our reference channel blocking. So for instance, like I said, some of these channels or sensors have a lot of charge inherently on the surface, such as carboxyl or NTA. So what we mean by referencing this channel, blocking this reference channel, is that we will probably, or we advise that you use a control protein to saturate that channel so that our analyte does not bind to that portion of the sensor. Now, another reason for this is especially for using smaller molecules as our analyte, we want to make sure that we're not seeing any bulk effects from that molecule. So we do recommend that both channels have a similar density. So your reference protein or reference molecule in the blocking channel and the reference channel should have the same ligand immobilization level as the ligand in your active or ligand channel. And I'll talk about that when we get to the ligand section again also. So what are some of these factors that we should be worrying about with respect to false positives? So like I said, nonspecific binding is one of them. So what is NSB? This is when our analyte sample itself is physically binding to other portions of the sensor surface other than the ligand that it's supposed to be binding to. And what's going to happen is this will lead to a false positive response. So you're going to see an increase in the response when this analyte is not specifically sticking to other portions of the sensor. And again, that comes back to the mass on the sensor surface has now been increased because of this interaction. So we're seeing this increase in binding response. So what do we do here? Well, first, we should be setting up a test to test for this so that we can combat it and optimize it. This can be done a variety of different ways depending on what instrument that you have. If we're using a one-channel instrument, whether it's the original instrument we have or a new one-channel instrument, we will be setting up an experiment where we're using a sensor that has no ligand immobilized on it. So in this case, again, we might have to use one of those blocking molecules. So we'll either leave the sensor untreated, we'll activate and block it with that blocking molecule, or in the case of, say, an NTA sensor, we'll immobilize a his tag protein that doesn't interact with our analyte. If we do have a two-channel instrument, we can observe these changes in our channel 1 response. So what we mean by that is the channel 1 in our two-channel instrument is always referred to as our reference channel. So if we see a response change in that channel, then we'll know that we are exhibiting nonspecific binding. Now, how we run these tests is once we have that reference channel or reference sensor set up, we will then inject our analyte at the highest concentration that we're going to use in our experiment, and we're going to see if we have any response change. So say, for instance, you have 5 concentrations of your analyte. The highest concentration you're going up to is 100 nanomolar. Then you will prepare that 100 nanomolar sample, you will inject it into the instrument, and you will look for a response change. Now, it's very common to see a response change. Nonspecific binding is very prevalent in a lot of experiments, regardless of what instrument you're using. So if that is the case, we'll then go back and optimize our conditions. So again, here's where some of that background literature search will come into play. If, for instance, your analyte is highly negative or highly positive, and we know that either the blocking molecule we're using or the surface of our reference channel has an opposite charge to that, then we might want to change the blocking molecule we're using, or potentially increase the salt in our solution so that we can optimize for this nonspecific binding. Once you've determined the change you're going to make, you'll then prepare a new running buffer with those conditions. You'll then reprime the instrument with that running buffer, prepare your analyte in that new running buffer, and then run that experiment again to see if that response change has been minimized. So what we have here is an example of how that experiment can be run. Here we've run a simple experiment on a carboxyl sensor. We see here that we've activated with our ADC NHS. We've skipped our ligand step and gone straight to our blocking molecule step. So now we have a sensor surface that is blocked with our blocking groups. We've now, in this situation here, chosen an analyte. This one was done at 100 nanomolar. We've done an injection with a simple running buffer that just has tween in it. And we see that we have a response change. So that we want to try to reduce before we go on to running our test. And then we can do this by adding different additives to our running buffer, such as increasing that tween 20 concentration. We can add BSA, we can add salt, or potentially other constituents, again, depending on what type of biomolecules you're working with. So what we've done first is we've increased the tween 20 concentration tenfold, and we see a reduction in that nonspecific binding. Now here, it's still higher than what we'd like to see, so we've gone again, and we performed another injection with salt added to our solution. We see that that salt hasn't caused much of a difference. So again, we go back to redesigning our running buffer. And in this case here, we've now added 0.1% BSA, and we see that all of that nonspecific binding has been optimized. So again, these control experiments are very important because as we can see from these first 3 injections, those look like semi-decent binding curves. However, they're false positives since we have 0 ligand on the surface. So this binding is not true binding to our ligand. Another thing that we'll find from these experiments, as we mentioned earlier, is that we might have to actually optimize the blocking molecule that we've used in the control channel. So in this experiment here, we use just our simple blocking solution, so in this case, ethanolamine. But we might find that we might have to actually use a control protein or something, or a blocking molecule that has a different charge. So say, in this case here, our surface is still slightly negative. If your analyte is quite positive, you might want to change that ethanolamine to ethylene diamine so that we can change the charge on the surface of our sensor. Again, when we're looking at these blocking molecules, we recommend that we try to get the density in this blocking channel to be identical or as close as possible to the density in our active ligand channel. So the next type of artifact or control that we want to run is for a bulk shift. So what is a bulk shift? A bulk shift is caused because of a buffer mismatch. So this is when the refractive index of our running buffer is different than the refractive index of the buffer in our analyte solution. So what this looks like when we run a test is it appears like this square-like function here. So we see a sharp increase, a plateau, and then a sharp drop in our response on our graph. So in this case here, this was done in channel 1 of a 2-channel instrument, so in our reference channel. So we know that this is a bulk shift because there's no ligand present in that channel. Now, there's various reasons why this could occur. It could be if your stock solution had, say, some residual DMSO or glycerol and you couldn't remove it all when you repaired your analytes, there will be some bulk shift that is remaining. And another thing could be is if you're using 2 different batches of the same buffer. So say you're using PBST as your running buffer, and then you prepared another 100 mils of PBST to make your analyte samples, there will be some minute changes between those 2 batches that will be visible in the experiment. So this is why we always recommend when you make your running buffer, you take that direct solution to make your analyte samples. So what would this look like if we actually performed an analyte injection over a ligand-bound surface? What we'll see is what we see in this blue response here. So we see we have what looks like a response curve, but at the end here we have what looks like a disconnect in the data as we're coming back down to our dissociation phase. Again, this is due to that bulk shift that is present in our sample conditions. If we do have a 2-channel instrument, this can be referenced out. So that's why we say, it's not always possible to fully match our 2 running buffers and analyte sample buffers. And this is why that reference channel would be important. Now, if you are using a 1-channel instrument, then it is imperative that we remove that bulk shift completely from our analyte samples so that we don't have any of this false positive data when we're going to fit our data after our experiment is complete. All right, so now that we've planned out our control experiments, now we can start thinking about planning our actual experiment. So the first thing we need to do is we need to immobilize one of these binding partners, so our ligand, onto the sensor surface. So for this step of the procedure, or of our experiment, we have a nice handy equation that will become quite useful for when we're going to plan these experiments. So what we have here is we have our Rmax value. So this is the maximum binding response that we can detect for our analyte, and it is proportional to the molecular weight difference between the analyte and the ligand, and that ligand immobilization level. So right here, even before we've gone to the lab to start our test, we should be thinking about, okay, well, I need to have a certain ligand immobilization level before I can continue with my experiment and get my analyte binding curves. So for an example, say we had a ligand that was 150 kilodaltons, so standard weight for an antibody, and we have an analyte that's slightly smaller at around 35 kilodaltons. When we go to use this equation, we see we still have 2 variables that we don't know. We don't know our ligand immobilization level or our Rmax. Now, here we want to put an estimate value for that Rmax. So we know the signal to noise is around 3 to 5 response units. We want to be at least 10 times above that. So we want to have an Rmax of at least 50. Now, depending on the interactions you're going to be working with, if you're working with 2 different proteins or biomolecules of similar molecular weight, you're probably going to be a lot higher than that. But we want to set that to 50. And then when we go to solve for our ligand immobilization level, with using these parameters, we'll get a value of 214 response units. So that means that even before we've started our experiment, we already have a number in our head that we would like to see when we're going to do our ligand immobilization. Now, if you're using our new 2-channel instrument, this will be built into the ligand wizard. So this will populate as you're running through the experiment. But again, we want to be thinking about this before we plan our test. So, because if you have not done an experiment yet, or you've done a few, we do recommend that you have our sensor chip tech guide with you to go through what the full ligand immobilization procedure would look like. And then you can start playing around with what kinds of numbers you would like to see when you run this experiment. So some ways that we can optimize that value or increase it if we're having troubles getting it high during our test. First one would be our pre-concentration test. So this is only applicable for amine coupling experiments. But what we're doing in these tests is we're using the charges that are inherent on the surface to increase our apparent immobilization level that we're going to be getting in the experiment. So for our carboxyl sensors, our surface is very negative. What we want to do is take advantage of our protein and manipulate it in a way that it'll now have a net positive charge so that it'll be electrostatically attracted to that surface and it'll increase the local concentration on the sensor surface. So this comes back to pre-planning when we go through our literature search and getting the PI of that protein. If we know what it is, we can then create immobilization solutions that'll be below that pH value, that PI value. So what does that experiment look like? It looks something like this. To do a pre-concentration test, we'll take a plain carboxyl sensor. We'll have no ligand immobilized there. We'll have it untouched. So no activation, no blocking, no ligand, just our plain carboxyl sensor. And then we'll prepare, in our case here, we prepared 5 solutions of our ligand. So in this case here, the ligand had a PI of around 6. We prepared 5 concentrations, starting from pH 4.0 up to 5.5, and then also using the activation buffer that's present in our amine coupling kit. So how this experiment works is we'll take our highest concentration, so pH 5.5, perform an injection, see a response change. That response change will be due to just the sample electrostatically accumulating on the surface. There is no coupling going on because the sensor is not activated, and then that ligand will flow off the surface, and that's why we see the response change come back down to baseline. After we finish that injection, we'll then regenerate the surface with HCl just to make sure that all of that sample has been removed, and then we'll increase on to our next lower concentration. So you might ask, why are we doing this? Well, the purpose of this is that we want to determine the activation buffer or immobilization buffer we're going to be using that gives us the highest response, so the highest pre-concentration on the surface. This will lead to the highest ligand immobilization level for our test. In this case here, we see that we have 3 samples that are around the same response change. So that is our activation buffer, our pH 4.0, and our pH 4.5 sample conditions. So what we do when we have similar responses is that we always want to take the highest pH value of those conditions. The reason for that is that we don't want to have our ligand at too low of a pH for too long, because that could cause issues like denaturation, less activity when we're going to run our test. So that's why we'll choose the highest pH out of those conditions. So in this case here, we would take our pH 4.5 sample or the activation buffer, they're similar pH, and we would use those conditions for running our test. Now, another thing that we might find, especially if we're using sensors that aren't carboxyl, so say NTA or one of our other capture coupling sensors, is that we might have to test out a range of different immobilization concentrations. So we usually recommend using between 5 and 50 micrograms per mil. So you might want to start at say 5 or 10 micrograms per mil. If you run that ligand injection and you see that you don't get up to that ligand immobilization level that you had determined from the previous equation, then you could either perform a subsequent injection at a higher concentration, or if you come back to do your test again, say you try with those conditions, did your Analyte samples, didn't see very good responses for your Analyte injections, when you go to do your next experiment, you'll then use a higher ligand immobilization concentration. So these are just things that we recommend, especially if you're using the carboxyl sensor, before you run your first test, perform this pre-concentration test. That way you know what the buffer conditions should be for your immobilization buffer, and then you'll be ready to get to that ligand immobilization level that you need for your experiment. So once we have that ready and we're going to do our actual experiment, here's an example of what the ligand immobilization looks like. So this is another one for carboxyl. We have here our activation step, the EDC and NHS. Then we go to our ligand immobilization step, and then our blocking step. What you'll notice here is that some of these steps don't happen in both channels. And the reason for that, again, is that we want to make sure channel 2 is our ligand immobilized channel, and channel 1 is our reference channel. So here we can see channel 2 has increased during the ligand immobilization step. Channel 1 stays flat, no ligand in that channel. All we want to see from this is that we want to ensure that that immobilization that we've achieved in that channel, so we can do that by calculating the difference from after the response to below the response, is high enough that we've reached that calculation that we had when we used the Rmax equation. All right, the next thing we're going to look at here is our Analyte sample conditions. So for this, what we're talking about is what concentrations of Analyte are we going to be using for our test. And these all come down to what the affinity is of our interaction. So if we have an estimate of that KD, so again, we go back to our literature search, we've seen someone else has worked with these two biomolecules, or your lab has used them, say using ITC or something, and you have a certain concentration for that affinity, say it's got a KD of like 10 nanomolar, then we're going to create a range between 0.1 times and 10 times that KD value for running these experiments. Now, if the KD was found using a different technique, we recommend expanding that range a bit because it might be slightly different, translating from, say, ITC to SPR. One, you're using binding in free immobilized solution. Another one here, we have an immobilized coupled partner, so we'll be slightly different. But that is a good starting point. If we have no information for the KD, what we recommend is starting at a low nanomolar analyte concentration and then increasing that response until we see a response observed on our experimental graph. So what we mean by that is we'd like to see at least between like 20 and 30 response unit change, so that indicate that we do see specific binding. And again, this is after we've done all our control experiments, so we know that this isn't due to non-specific binding or bulk shifts, and then we'll increase from there. So if we don't know a concentration range, I usually make my samples with a 10-fold dilution. So I'll start at around 10 nanomolar, 100 nanomolar, 1 micromolar, and try those 3 concentrations and see what kind of response changes I get. And then you can narrow into the correct concentration range for your analyte solutions. So the analyte sample conditions that we're going to use are going to be slightly different if we're doing a kinetic analysis versus a steady state analysis. So the difference between the two, the kinetic analysis, we're going to be getting full kinetics. So what that means is we're going to be getting information for both the on and off rate. And theoretically, we can fit all of these to one concentration. So if we have one binding curve, we can calculate an on and an off rate and then get our KD value. However, we recommend using at least 3 to 5 concentrations. The reason for that is that we'll have a much more accurate calculation for that KD value, and that'll become more apparent in a little bit here. But we do recommend 3 to 5 concentrations. And again, we want to be in that 0.1 to 10 times the concentration range, like we see down here. And to obtain that, we usually use a serial dilution. So I recommend doing a 3-time serial dilution. The reason for that is that with 5 concentrations, you'll be able to hit this 10 to 0.1 times the KD range quite easily. And this will make sure that we have nice spacing between our curves, and we've caught both the low and high end of that KD value. So on the low end, again, we want to see a response change that's around, quite low, 20 to 30 RUs. And again, that'll be dependent on the ligand immobilization value. And then on the high end, we want to see a curve that reaches saturation, or what we would call steady state, and then we start seeing our dissociation after that. Now, if this range is too high or too low, you might see some response curves like we see on the left and the right-hand side here. On the left-hand side, we've kept all of our analyte concentrations quite high, so we see we have nice binding curves, but they're all grouped at the top end of our KD value. So when we go to calculate that KD, we're going to get a value that's skewed slightly higher than it should be. On the right-hand side, we see that we have quite small binding curves. Now, again, those might actually be the situation depending on our analyte to ligand molecular weight. But to test if that's correct, what we would do is we would create another analyte sample at a much higher concentration and then perform a subsequent injection. If we see a response that has changed drastically, so 2 or 3 times that response change, then that would tell us that we're at too low of a concentration range for our analyte solutions. Or if we see that the response hasn't changed very much, then that means that we are saturated and we're at that high end of the KD range. So again, the sample conditions for our analyte solutions do become quite important when we're planning these experiments. Now, there is a slight difference if we're going to be only being able to determine an affinity analysis. So what an affinity analysis is we have a very fast off rate, which makes it quite challenging to deduce the on and off rate from our analyte. So it's so quick that it's hard to get an accurate off rate. So in this situation, the only thing we can calculate is an affinity concentration. And in this case, because of that, we're going to need to use 5 to 8 different analyte concentrations. The reason for that is each analyte response curve is going to equate to 1 data point on our concentration versus response graph. So we want to make sure that this concentration range covers the full range of our KD values. So we want to make sure that we have at least a couple of data points that are on the low end of our concentration signal graph and a couple that are on the higher end. And then when we calculate our KD value, this concentration range should be in the middle of that. So what we mean by covering a range twice the KD value, if the KD is, in this case, 75, we have values on the low end of 20, 30, and on the high end of a couple hundred. So make sure that we're not missing that KD value. If, for instance, your graph looks something like this, where the line's almost linear as opposed to curved, and our KD value that's calculated is at the top end of that analyte concentration range, then we wouldn't put as much faith or trust into that KD value, and we would recommend repeating the experiment and including some concentrations that are higher than what we use. So I would use 4 or 5 of those concentrations and add 3 more that are higher, just to ensure that we're getting the right KD range for our experiment. And the last thing that we might have to decide on when we're running these tests is if a regeneration solution is needed. And now, again, one way to decide on this is our literature search that we've done. If other experiments that have these 1 or 2 of these analyte or biomolecules have been used, they've needed a regeneration solution, then it's quite likely we're going to need one here. And again, you'll also know about that too, depending on other work you've done with these biomolecules in the past. But the main thing that the regeneration comes down to is the off rate of our analyte, or the off rate of our interaction. So what we mean by that is if we have an interaction where the off rate is quite fast, so when we get to the dissociation period, our response comes back down to baseline quite quickly. In that situation, no regeneration solution would be necessary, so you can just simply go on to your next analyte concentration injection once we get back to baseline. If you have a situation where we have what we call a slow off rate, so in the dissociation phase, the response is fairly horizontal, would take a long time to get back to baseline, that is when a regeneration solution would be necessary, and we might have to then decide what we're going to use for that. What this regeneration solution is going to do is it's going to dissociate all of these analyte molecules from our ligand, because we need to make sure every analyte injection that we're doing, we have the same number of ligand binding sites available for that analyte to interact with. If some of those binding sites are occupied or saturated, then our response curve will be smaller than it should be, and it'll lead to incorrect or inaccurate kinetics when we go to fit this data later. So essentially, when you do your analyte injection, you'll get your nice binding curve. Say we don't come back down to baseline, we use a regeneration solution, and then that removes all the analyte, and our baseline should return to where we started before that injection. So what kind of regeneration conditions are we going to use? Well, what we want to make sure is that whatever one we do choose, it disrupts this analyte ligand binding and removes it from the surface. Again, this is so that we can have the same number of ligand binding steps available. And for this to occur, there are quite a few different regeneration conditions that can be used, and these will all depend on the interaction of your analyte and your ligand. So again, it'll come down to what type of interaction is occurring. And if you have been using these in your lab before, or again, through your literature search, if these pair have been used before and a certain regeneration condition has been used to successfully disrupt that binding or to dissociate those two partners, then those conditions can be used here. These conditions are completely dependent on the binding of your two biomolecules. Has nothing to do with the instrument. So if, for instance, a lot of antigen antibody binding, you can use glycine HCl solutions to disrupt that binding, and then you'll be able to regenerate your surface and go on to your next analyte solution. Now, what if you've checked the literature and you can't determine a regeneration solution? In that situation, we would perform what we call a regeneration scouting test. So for this test, it's quite simple. What we would do is we would prepare multiple solutions of our analyte sample. In this case, the concentration we'd be using would be one that is at more of the saturating end. So again, if we know that 100 nanomolar, we have a nice response curve when we interact with our ligand, we'll prepare multiple samples of that. So I like to use 5 samples so I can try 5 different regeneration conditions. So in our case here, each sample that we inject is 200 microliters. I would make 1 milliliter of that concentration of analyte. That way I know I have 5 identical analyte samples. And then I'll prepare various regeneration solutions. So again, even before I start this test, I'm thinking about, okay, well, if I'm using protein, maybe I'm using an acidic solution to try to regenerate this, and so on and so forth. So I'll have various different types of conditions planned out. And in this case, I'll choose 5 of those regeneration conditions. To run the test, what we would do is we would inject our first Analyte solution, so one of those 5 that we prepared, followed by one of our regeneration solutions. We'll then look to see, has the response come back down to baseline? If it has not, we'll repeat this. We'll do another Analyte injection, followed by one of our other regeneration solutions. What we recommend is that you start with the mildest condition first, and then increase the harshness of these regeneration solutions. The reason for that is, again, we're going to be hitting these ligands with our regeneration solutions, so they're going to be interacting for a specified amount of time. We want to make sure that we're not damaging the ligand also. So we want to make sure that the binding has been removed because we've dissociated the 2 compounds, and not because we've destroyed our ligand and now binding cannot continue. So during these tests, we'll be seeing some results like we see in the bottom here. If the condition is too mild, you'll see that we have a nice Analyte response. After the regeneration, our baseline does not come back down to where we started. So we'll then perform our next Analyte injection. After that next Analyte injection, if we see that that baseline comes down to below where we began, then we probably use too harsh of a condition. So what could have happened here is if we're using, say, a capture coupling method for our sensor surface, we might have actually removed some of the ligand from the surface, or potentially we've denatured some of the ligand, which changed its conformation on the surface, which caused this baseline to be lowered. And then our subsequent Analyte injections are no longer going to have the same activity that the previous ones have. What we'd like to see is something like this. Our Analyte injection is performed, our regeneration solution is done, we get back down to the same baseline. When we perform our next Analyte injection, we see the same response change, so that signifies the ligand has not been damaged, and we had the same number of ligand binding sites available for this Analyte to interact with. So hopefully when you've done this scouting test, you'll then have the conditions that you will need for your interaction to be removed. And the last thing to do is, if we have found that we do need to use a regeneration condition or solution to dissociate our ligand and Analyte, we recommend that you condition the ligand surface prior to our first Analyte injection. So what that means is, I'll show you in this experiment here. We have our ligand immobilized via his tag on our surface here, and we're going to do a regeneration injection before our first Analyte. What we can see here is that the baseline has lowered. Now, we also saw before that the baseline had a slight dissociation or off rate, and here we see it's a lot more steady. It's steadier than it was before. So what this is signifying, or the reason we do this, is that during our ligand immobilization step, again, a lot of these are occurring due to charge interaction. If the ligand isn't fully coupled to the surface but is loosely associated because of some slight interaction with either another ligand or parts of the surface, this regeneration step will remove that. And that usually helps stabilize our baseline. And then we also see that after each subsequent Analyte and regen step, we come to the same baseline. So that suggests that we've chosen a suitable regeneration condition to fully remove that Analyte, but keep our ligand activity in check. Awesome. Well, that is all of the steps that we would cover when we're going to design an experiment, and all the steps we would use when we run an experiment. So what we've like to challenge you with right now is, if you can or cannot get to the lab, this is still a good time to be thinking about those experiments, because we know these projects must continue. So we challenge you to come up with a new experimental setup for you to use and try that once you can get back into the lab. And we invite you to email it to us, and we can give you a hand either optimizing that experiment or just giving you reassurance that what you have chosen to do would be able to work out quite well. So good luck with the rest of your researching. And again, if you have any questions, I invite you to post some in the chat box now, and then we can go over them together. So feel free to type away. And if you don't have any questions at the moment, what we can do is, feel free to email us. We can converse via email. Other thing we have also is our support portal, where you'll find a lot of information on the different conditions you might want to use for your test, and other All right, we have one here. So what is the buffer used for pre-concentration? That's a great question. So it depends, again, on the PI of your protein. Typically, what we would recommend is using an acetate buffer and preparing different pHs from pH 4 to 5.5. If if the pI of your protein is higher than that, say it's like 7 or 8, then you might just want to use a simple phosphate buffer. Now, one thing to keep in mind is you want to keep the salt concentration low because you want the ionic strength to be low because we don't want to be shielding those electrostatic effects on the sensor surface because then in, that'll lower the pre-concentration effect, so it won't help with our conditioning for that test. All right. Next question here is there an easy way to tell when the chip needs to be replaced? That's a good question. Now, this can be, I guess, a couple different ways to interpret that. So I would imagine if, for instance, say you have a sensor where you've covalently coupled your ligand, so carboxyl sensor, that sensor, obviously, you cannot reuse it. That ligand has to be used all the time. What I would recommend is if you're running multiple tests over multiple days, I would use the same analyte concentration that I used on a previous day and see if I get the same response. If the response will probably be hopefully somewhere in the same area. If the response is drastically reduced, then it could be that that ligand has either lost activity because it's been sitting for so long or has not been or can't be used anymore. If you're using, say, a capture couple sensor, what we recommend is at the end of that test, you fully remove your ligand. So the sensor is now bare, whether it's NTA, GST, lipid sensor. And then when you come back to do your next test, so you're going to use it again, see what the ligand immobilization level is. So for instance, if your ligand has a similar molecular weight as the previous one, or if you're using the same ligand and same concentration, you should get a very similar RU change or ligand immobilization level. If that level is a lot lower than it should be, then that probably means that either the surface wasn't regenerated well enough before and some of the previous ligand had aggregated on the surface and now is no longer active, or the sensor surface itself might need to be changed or replaced. Okay, in the last slide, what does it mean when you see decline during the analyte injection? I assume that means, I'll go back to that last slide and then we can. All right. So if you're referring to it at the top here where it says slight off rate, what that means there is that some of the ligand is slowly dissociating from the surface. So this could be due to a number of factors. In this case here, since we're using an NTA sensor, actually, sorry, you can't see the screen that I'm looking at. Let me change that over for you. Sorry, 1 second here. So here, this part here where we see this slight off rate, what that means there is that the ligand is slowly dissociating from the sensor surface. So this could be one of two things. A, like I said in the talk here, this could be because there's some ligand that's still loosely associated to the surface. It could be because you use such a high concentration when you immobilize the ligand. And this isn't actually coupled to the sensor. So the his tag isn't interacting with the NTA. So some of that is coming off. If you do this conditioning step and you don't see a steady baseline, then it could just be that his tag interaction with the surface isn't as strong as we might need it to be for this interaction. So you'll probably have this off rate throughout the duration of the experiment. In that situation, it might be better to switch to maybe a covalent coupling method. So, since we're using a protein here, we can easily amine couple this to the sensor surface. Now, if you're talking about this dip here that we see throughout all of these analyte injections, those are just the regeneration injections. So because our regeneration solution has a different refractive index than our running buffer, we're going to see a bulk shift. So those are just bulk shifts from our regen solutions. In this case, we use sodium hydroxide and the running buffer was PBS. So the different refractive index is causing that change in the response. Oh, I see what you're saying. The off rate increases as okay. So what's probably causing that is that the concentrations we're using in these later injections are actually too high. So we're above that saturated concentration that we're at. So we're seeing whatever analyte is there coming off very quickly because it's oversaturated, and we see a faster off rate there. So again, this is where when we're analyzing these concentrations when we're doing our fit, we would probably modify the concentrations we would use for this interaction. As we see here, all of our analyte injections give a pretty healthy or pretty high change of response of a few hundred RUs. So we would probably re-optimize this experiment and use some much lower concentrations of analyte so we get that lower end of the KD value. All right. Do we have any other questions from anyone else here? Oh, here we go. Okay, good question. Yeah, so if you're using an amine sensor, we would definitely recommend that whatever ligand you're using, you would activate in its own like tube. So you would have your EDC and NHS, you would activate that in with the ligand, and then yes, that would probably you would use a buffer that would actually no, that one won't matter too much if the buffer doesn't the pH is different. But one thing to note with the amine sensors, and if you're going to activate a ligand with carboxyl groups, is we recommend using these for situations where the ligand only has one or a couple of carboxyl groups that are not in the active site. So the amine sensor might not be a great choice for protein work. The reason for that is any carboxyl on that protein will now be activated with EDC and NHS. So it can immobilize onto the amine surface in any conformation. And then when you go and add your blocking solution to then deactivate those surfaces, you're now modifying the ligand, in this case the protein, with that blocking molecule. So that could lead to inactivation or of the protein from binding to your partner. Now, if you're using, say, a small molecule that's been modified with a carboxyl group so that you can bind it to an amine sensor, I would just activate that in standard, probably PBS, or not PBS, probably phosphate buffer, pH 7. Again, I would leave the salt as low as possible so that it doesn't shield our charges when we're going to immobilize it to the surface. But these small molecules probably have a higher pH, a PI, so you probably, or higher charges, so to speak, more positive. So you'll want to adjust for that. So in that case, no, you're not required to use the activation buffer. If you are, say you're using small molecules, then we do have an amine coupling kit for small molecules, and it does have a buffer with a higher pH that is optimized for using these higher or these more positively charged molecules when you're immobilized to the surface. Great. All right. Well, again, if you do come across some questions when you're going to plan your next test, please feel free to reach out to us. Again, you can contact us at support@nicoyalife.com. We're always available to help you optimize your experiments, or even if you're in the early planning stages and you're not sure of some of the steps that we discussed here. If you're not sure what sensor to use, we can help recommend the correct one based on the biomolecules you're working with. If you're still a bit uncertain of what like a control test you can run so that you can be satisfied when you're going to look at your results, we can also help you with that. Yeah, basically anything that you need with respect to your experiments, we're able to help you out with. So with that, then, we'll probably end today's webinar, and we look forward to seeing what type of experiments you come up with, and always love looking at the nice data that you've generated. So feel free to reach out to us, and we'll talk to you on our next episode. Thank you for joining us. Have a good rest of your day, and everyone stay safe out there.